Welcome to Brain Vision.
Hello everyone, I'm doing problem 30 of chapter 31. This question concerns the proton-proton chain, which is a fusion reaction describing the energy output of our sun. So the question refers us to formula 31.6, which I've reproduced here, which gives us three reaction equations that describe the fusion process. And each one has each reaction here is associated with a release of energy given in brackets here. And this released energy is in fact the Q value that the question is asking us about. So we're also given some values from the appendix, which I'll discuss in a moment. And we know that Q, the energy, is associated with delta M, which is the difference of mass between the elements or the items on the right side of the arrow and the mass of the elements or the components on the left side of the arrow, multiplied by the speed of light squared, c squared. So for this problem, we're basically budgeting energy, and we can rewrite these reaction equations in terms of Q here. So let's start. Write the Q value for A. So we're going to do the masses, the energy associated with the masses on the left side minus those on the right side. So here we have two protons. Let's say 2m sub p multiplied by c squared minus the mass of deuteron sub d times c squared minus the mass of the positron, which is in fact equal to the mass of the electron, by c squared. And the neutrino doesn't have an atomic mass, so it doesn't show up in this equation. And now we can see the c squared is present in every term, so we can factor that out. So I'll just quickly rewrite this. And now we want to look at our numbers from Appendix B to fill in the values. So I will convert to text for readability. And we want to be careful here because the text of the textbook tells us that we're dealing with nuclei here. So we don't want to take the H quantity because that includes an electron. So here we really want the mass of the proton. X means times. And this is given to us in atomic mass units U, and we always want to be sure to mark the units because it can really keep us from making mistakes. And we'll take the deuteron. And the electron mass. Oh, already forgetting my units here. We want all of this to be multiplied by c squared. And now you'll note that our units are in atomic mass units times c squared, whereas our final answer, we're looking for it to be in megaelectron volts. So we'll need a conversion factor, which is 931.5 electron volts per c squared per u. And so you can check that the units all cancel out to give us the result in megaelectron volts. And you can put that into a calculator and verify that it does in fact equal close to 0.42 megaelectron volts. Equals approximately, I'll do a curly equal here. Now for B, we proceed in a similar way, where we write our equation, our expression for Q by subtracting the items on the right side of the arrow from those on the left side. Now, you'll notice that this time I'm marking M sub H for hydrogen, and I will explain that in just a moment. Plus a mass of deuteron, but again, I'll put deuterium instead of M sub D as I did up here. This isotope of helium. So before we fill in the numbers, just a subtlety here. We're dealing with nuclei, but for the case of helium, which I'm sorry is cut off here, but I'll enter the values in a second and you'll see them. But for the case of helium in the appendix, we are only given the atomic mass, which includes electrons. But since electrons in this equation are balanced, that is, the nuclei on the left side of the arrow are each associated with an electron. So this side, there's, if we're including electrons, we have 2 electrons, and the nuclei over here is also associated with 2 electrons. So we can add 2 electrons to both sides of the equation, and they cancel out. So that's why we were considering the mass of hydrogen here and not just the mass of the proton. Similarly for deuterium instead of just deuteron. So let's fill in our numbers. Oh, and again, gamma doesn't factor into the mass part here. Minus the mass of helium, which is 3.016029 atomic mass units. And we'll multiply all of this by c squared, and again by our conversion factor to get mega electron volts. And again, we can put this into our calculator and obtain a Q similar to 5.49, or essentially 5.49. Great. Now for the final equation, let's do C. Again, write our expression for Q. We have 2 times the mass of this helium isotope. Minus the mass of helium, times C squared, minus the mass of helium. Minus 2 times the mass of hydrogen, where again, we note that the electrons are balanced here, so we can add the electrons and subtract them here. So we will take the mass of hydrogen. Let's fill in the values with Appendix B. I'm just going to, hopefully you don't get confused, I'm going to try to enter them here, just for the sake of visibility up above. Minus 4.002603 U minus 2 times 1.007825 U. Again, multiply everything by C squared and by our conversion factor. And putting that into our calculator, we should get a Q value. Sorry, it's a little bit cramped here. A Q value of 12.86. Mega electron volts.
Welcome to Brain Vision.
Hi everybody, so we need to calculate energy released per gram and also calculate the energy released per gram of uranium in a fission, and we have to give a ratio, okay? So first, let's write out the reaction. So we have 2 deuteriums, so 1, 2 hydrogen, 1. There we go. And we have 3, 1 each, and that's a deuterium, and plus 1 hydrogen. Okay, and we have a 0.03 MeV. So we need to find the number of nuclei. Oops. Need to write number a little bit better. There we go, nuclei, and that's going to be N equals Avogadro's number, the mass, and the Na the mass of the other one. So we have per gram, and for this we have the Avogadro's number 6.23 times 10 to the third per mole. And then we have 1 gram, and then we have 4 grams per mole. Okay. And so that's going to equal 1.505 times 10 to the 23rd reactions. So this is our number required. Okay. And so to find the total energy released with 1 gram of fuel, so total E released with 1 gram of fuel, we are going to do 1.5, and we put that, and really it's for the energy, okay? And I can easily just do, there we go, guys. Fixed it. So we're going to take what we did right here and put it here, times 10 to the 23rd. And we're going to times it by the energy that we have up here. So that's going to be 4. I just realized it's not like 4. There we go. 4.03 MeV. Okay. And so what we get is 6.07 times 10 to the 23. And that's going to be MeV per gram. And let me just put per gram. There we go. That way you guys can see it so you're not confused. Okay. And now we're just going to go down just a little bit because now we got to do the second reaction. So I'm going to put second reaction here. And we're going to put this as the first reaction. Okay. So for the second reaction, we still have the same right here. And we have 6.023 times 10 to the 3rd mole times 1 gram. And if you're curious why this is it's because this is the other deuterium, okay? So this is the other deuterium in the reaction. And we know it's going to equal about the same. So let me just, there we go. 23, and it's reactions. Okay, and so now we just got to find the total energy released with 1 gram. And the energy is going to be different for this. So this does have a different energy. And so the energy, and you can look up in the appendix for if you want, is going to be 1.5057 times 10 to the 23rd. And the energy for here, if you look in your appendix, it's going to be 327 MeV. Okay, and so we're going to have 4.92 times 10 to the 23rd MeV gram. Okay, and now we got to do the third reaction. And again, this is still under 1 gram. And we have N times Avogadro's number, 6.023 times 10 to the 23rd mole times 1 gram. And this one's going to be 5 grams per mole. Okay. And for this, we're going to have 1.2046 times 10 to the 23 reactions. And again, we have, it looks like we have 17.59 for our energy. So it produces 17.59. We have 1.2046 times 10 to the 23rd times 17.59, which is in the appendix. And this is going to be 2.12 times 10 to the 23 MeVg. Okay, so there we found the energy release per gram of the reaction. So what I can do is, that one's for the first reaction, because it asks for per each energy released. And for the second reaction, we have this. And then for the third reaction, we have this. Okay? And yeah, so let's go to part B. And part B is asking us to calculate energy release per gram of uranium. So here we have N, and it's going to equal Na, so the Avogadro's number, and let me just write the Avogadro's number down for you guys, just in case if you haven't memorized it yet. I know for some people it does help having all the numbers written out. So 6.23 times 10 to the 23rd mole, and this is going to be 1 gram again. And for our uranium, it's going to be 235, because that is the mass of the uranium. So we have uranium 235.92, and that's just going to be this. Okay. And so from this, we get 2.563 times 10 to the 21 reaction. And now we have to times it by what we have in the appendix. So find the energy. So we get 2.563 times 10 to the 21 and times 200 MeV, and we end up with 5.13 times 10 23 MeV gram. Okay, now we got to find the ratio. So we found the energy release, so that's for the first part of B, and now we got to find the ratios. So we have the ratio for the first reaction, and that's going to be 5.13 times 10 to 23 MeVg. And now we're going to divide it by 6.07 times 10 to 3 MeV divided by V, and we're going to get 0.844. Okay, and this is from the first reaction. So this is a number we found from the first reaction. Okay, and now for the second one, and again, we are just using at the bottom the numbers we found above. Okay. And we'll put ratio here. Ratio. Here we go. And for this, we have 5.13 times 10 to the 23rd MeV. And then for the second one, we had 4.92 times 10 to the 23rd MeV. Okay, and we end up with 1.044. 5. And now for the third reaction, the third ratio, we have 5.13 times 10 to the 23rd MeV divided by 2.112 times 10 to the 23 MeV. And we can break this down a little bit to have it easier for you. So really what you're doing is dividing it by 5.313 divided by 2.12, your calculator. And that's because this cancels out with this. And then this cancels out with this. So you're really just dividing this together, okay? And so we have 2.4198. And we want it to match this. You see how I have 3 here, 3 here, and you can't quite do that. So we're going to do 2.420, okay?
Welcome to Brain Vision.
Hi everybody, so we want to know how much energy is released with uranium if it absorbs a slow neutron and becomes 239 uranium. So here, let's draw the reaction of what it's talking about. We got 238 uranium. There's a little 92 down here. Okay. And a slow neutron. So we got 1, 0 neutron. And they gave us 239 U, and it's 92. And let's just make sure that everything's balanced. So this is 239, 239, okay, 92, 92. Looks like it's balanced. So let's continue. We want to know the energy release. So we have MU, and let me put energy here so you guys don't get confused. Oops. We got the energy. MU plus Mn minus the atomic mass of U, of uranium. Okay? So here we have 238.07 plus 1.00865 plus, not plus, minus, there we go. Sometimes you just can't do things fast, guys. 239.054.288. Let me make sure that 4 is there. Okay, and we have U here, because I'm taking the U out, C squared, and we're actually going to times it by 931 MeV divided by UC squared. And if you notice something before you plug it in, you're going to notice this is going to be a small number times this, because this is a 239 and it's subtracting from a 238, and this 238 is going to be about 239 something. So this shouldn't be that difficult to do. And after you multiply everything, plug it in your calculator, you have 4.07807 MeV. And that is your energy released. Okay? Let me put energy released for you. Energy released. Okay, guys, I hope that helps.
Welcome to Brain Vision.
Hi everybody. So we have a house that has 960 watts of electric power. And we want to know determine the fuel that would have to be used in a year to supply the electrical needs of this house. And we're also given this equation, this reaction, there we go. We have the two deuteriums and the helium. Okay, and we have the number of reactions is N equals power times time over energy, okay? And we also have M, F, and this is the minimum amount of deuterium fuel, which is equals 2 times N times the mass of the deuterium. And we can plug this in, so we have 2 P T over E times N. Okay? So now I'm just going to plug in the information that we have. So we have 2 times 960 watts. And we need to convert this to joules per second. Okay? And we have a time of 1 year. And we're going to times this by seconds. So 3.15. 36 times 10 to the 7th second. Or we can just put as S. There we go. Year. Okay. Over this thing. And we have 3.27 MeV. And we're timesing this by 1.6 times 10 to the negative 22. There we go. Negative 22 joules over MeV. Okay. And now let's put the MED of the mass of deuterium, and we have I'm just going to put little brackets here. 3.35 times 10 to negative 27 kilograms. Okay. And now you're just going to go here, and we're going to put everything into our calculator. And after we do that, and before we do that, let's do the signs for you guys. So that way we can use that. So we have years taken off. We have watts taken off. We have MeV taken off. And this becomes, we have the joules per second. So we end up with the joules second up here, second up here. And then we have joules down here times this kilograms, and we see how this all cancels out in these kilograms. So your answer should be in kilograms. Okay, so after we plug in all that into our calculator, you should get 0.00387,690 kilograms, or you can get, if you put this into grams, so this is your kilogram answer, okay? Okay,
Welcome to Brain Vision.
Hi everybody, so we need to find the second nucleus and how much energy is released in this problem. So we have A, and we're given 6 lithium, 2, 3, and has under a slow neutron. So let me write that a little better. So we have a neutron here. And we're also given the helium. 2. Okay. We'll put plus. So we have 3 here. If I write this a little nicer for you. We have 3 and 0 here. Since this says 3 and this is 2, we know we need 1 here, okay? And we know that this is 6 plus 1, which is 7. And so we need 7 over here. So we have 4. So what plus 4 equals 7? And that's going to be 3, okay? And it's going to be 8 hydrogen, okay? And that's your missing link. Now for B, we need to find how much energy is released. So we have this. And remember, it's from right to left, left to right. There we go, if I can speak. So we have lithium 6.015. 1, 2, 3. U plus 1.0086665 U minus 4.002603 U minus 3.01609 U. And we have a C squared here. But I'm going to just times this by the 931.5. And this is MEV. And oops, and not do that. U C squared, and we have the C squared here. Okay, and I'm just going to put so you guys can see we have the MEV there. Okay. And here, if we plug and chug into our calculator and times it by 931, we should get 4.784 MeV, okay? And I don't know why I put in brackets. There we go. And that is your answer for part B, okay? Thank you.
Welcome to Brain Vision.
So we have a fusion reactor that runs on a deuterium-deuterium reaction, and we want to estimate how much natural water is needed per hour to run a 1,150 megawatts reactor, and assuming 33% efficiency. So we have 2 possible reactions. I'm going to call this A. Oops. If you guys can even read the A, there we go. A plus the other deuterium. Okay. And this could be 1 hydrogen, 3 hydrogen plus 1 hydrogen. Okay. And this one has an energy of 4.03 MeV. And here we have 2,1H deuterium plus 2 deuterium. And we have 3 2 helium plus the nitron, and it's going to be 3.27 MeV. So if we have 4.03 MeV plus 3.72 MeV, we receive 7.30 MeV, and 5, right? Hold on. Oh, that's 27. My bad. That would help if I wrote it right, guys, not backwards. There we go. You guys probably thinking that was crazy. There we go. Now it matches. And this is the total energy released. And if we subtract them, we get 1.825. And this is energy released per deuterium. Okay, so now let's go back, go down, and continue with our problem. And we have power is going to be 1,500 watts. Over 0.33%, which is the percent they gave us. So we have 3.485 times 10 to the 6. And now we need to find the number of deuterium atoms. So we have N. And that equals the power that we have. So we have 3.485 times 10 to the 6 times 1 hour, which is times seconds, 3,606 seconds over hour, okay, times 1.825 MeV. And this is going to give us 4.296 times 10 to the 25th. And we have deuterium here, okay? Now, we need to find the mass for the water. So we're going to go back down here, and we're going to try to write this as small as we can so we can fit everything in. So we have the mass that we just found. Okay. Now we have number of H atoms, so 1 H atoms, hydrogen atoms, divided by deuterium found in water, 0.00115 gram. That's the average deuterium found in water, okay? Times water, which is H2O, and 2 hydrogen atoms, okay? And now we're going to times this by a mass of H2O, 0.018 kilograms of H2O, and divide it by Avogadro's number, so 6.023 times 10 to the 23 mole. Okay, and now we've got to check if these cancel out. Okay. And okay, so we have kilograms of H2O, and we don't need to worry about that. Okay. Moles. Okay. So we're just gonna check it. And we got 1.86804347 times 10 to the 29th. 1 H2O times 0.018 kilograms H2O. And we have Avogadro's number. Okay. And so the water that we need, the amount is going to be 5.58 times 10 to the 3rd kilogram. And that is your answer, guys. Thank you so much.
Welcome to Brain Vision.
Everybody, so we need to show that the energies carried by the helium are about 3.5 MeV and 14 MeV. Whether or not they're independent or dependent of the plasma temperature. So here we have this reaction. Oops, let me write it a little better. So it's 3 hydrogen, 1 equals 4 to helium plus nitrogen. Not nitrogen, neutron. There we go. And we can find the energies here by doing left minus right. And that's the atomic masses here. So 2.014102 plus 3.016049 minus 4.00263, just 3, and plus 1.008665. And we can do UC squared out here. Okay, so that's going to be 5.03051 U minus 5.01128 U times C squared times 931.5 MeV C squared and U. Okay, and so your answer is going to be 17.59 MeV. Okay, and we're going to go down here because we got to find the energy carried away by the helium. And so we have energy of helium here, so carried away energy. And we have the mass of the neutron, the atomic mass of the neutron, 0.1008665. And now we got the total mass up here and on the right, on the right hand side, which is going to be this. Okay, so we get 5.01126 U here, and times our energy that we found, so 17.59 MeV. This is going to give us 3.54 MeV. Okay, and then the next one, we got the energy carried away by the neutron. So now we need the helium mass here, so it's 4.02603 divided by 5.01128 UU times 17.59. And I can put MeV too. Let's not forget that. And EV. And this is going to give us 14.049. And we can change that to 3.5 MeV. And we can change this to 14 MeV. And that checks out. And this is going to be dependent on plasma temperature, okay, guys? And I hope everything helped, and hope you have a nice day.